Okay, now I'm recording. Hello, all MAT136 students. So this is like the makeup recorded lecture for today's lecture, which university was closed because of winter storm. And the topic that we are going to discuss is partial fractions, one of the very important techniques of integration. First, what is the idea of partial fraction? It's integrating a rational function. What is a rational function? It's a polynomial function over polynomial function. So we want to integrate a fraction which both top and bottom are polynomials. That's what we do today. All the session is about this. So first, let's start with some warm-up questions that we can do that without new lesson. So how can we compute this? It should be easy for you at this step that guess that I should take this as my new variable u and do a substitution u equals 5x minus 2. Then du will be 5 dx. And if I do this substitution here, that is u, and this is dx. dx is solving from this, it's 1 over 5 du. 1 over 5 du. So this integral is the same as 1 over u times 1 over 5 du. Then computing antiderivative of 1 over u, it's ln. So the answer is 1 over 5, this coefficient, ln absolute value u plus a generic constant. But my original function was in terms of x. I should express it in terms of x. I will replace back u in terms of x, and I would get ln absolute value 5x minus 2 plus c. So I think D is the correct one. Good. And next warm-up question. So we already found this 1 over 5 ln. This comes from the previous computation. Now, we also can do this if you remember in one of the lectures, we had a formula that x squared plus a squared integral of such thing is 1 over a arctangent x over a plus c if a is positive. We had such formulas like this. Using that formula, we have this with a equals 2. That's coming from one formula in the substitution section. Even if you forgot the formula, you can still compute it. How? By doing a substitution. First, factor 4 out of this. You can factor 4, then you get x squared over 4 plus 1. And this is the same as x over 2 squared. So you know that you should take x over 2 as a new variable and do a substitution. Then you can use arctangents. So you can these formulas that I just mentioned, they are coming from just a simple substitution. Anyway, we have these two. Now the power of partial fraction comes in. What happens if we want to integrate this, find antiderivative of this? In this form that we see, we have a polynomial of degree 2 quadratic on top and polynomial of degree 3 on the bottom. And I don't know how to find antiderivative of such thing, a fraction of polynomial over polynomial. But if I have a mechanism that gives me this fraction as sum of these two fractions, which are simpler, these are called partial fractions, the method of partial fractions. The idea is writing a fraction into a smaller fraction, but simpler fractions. If we will see how we can do that. But at the moment, just assume that we have this partial fraction sum. So if you assume that we have such thing, then computing antiderivative of this will reduce to two smaller problems, finding antiderivative of this and antiderivative of this. If I know the answer of these two separately, then I add them and I get the answer, which I know in this case, it's this and this. I add them and I get the answer for the original function. So I can say that antiderivative of this fraction is the same as using this equation. Antiderivative of first fraction plus antiderivative of second fraction. For the first fraction, antiderivative is this. It's 1 over 5 ln absolute value 5x minus 2. For the second fraction, the answer is this. 1 over 2 arc tangent x over 2. And don't forget to add a generic constant for the whole integral. I only need one. It's only one indefinite integral. I only need one extra constant and I add it. So that would be my final answer. See, it's like a kind of questions that it's divide and conquer. So you divide your like harder and a larger problem into a smaller pieces that I can handle, and when I have answer for all of them, I have answer for the whole question. That is the main idea of partial fractions. So basically the key step is this step. How do I break a fraction into a smaller fractions, which are called partial fractions? That's what we discuss next. So first we start with a rational function, which is a polynomial over polynomial. So each px and qx are polynomial functions. Then I need to write the partial fractions terms. First, I need degree of top to be smaller than degree of the bottom. So if the degree of top is more or even equal, I need to do long division. That is what you learned in high school. We won't review it, but as just a quick recall, we have something that we put Q here. It's a process that you put here, Q here. You put P here, and you do some operations. At the end, you will find some remainder and some quotient. This process is called the long division. You should know it from high school, but good thing is that we usually design questions in this course such that it won't need long division, or if it's long division, it's something that you can do it without knowing long division, to have like minimum dependency on long division technique that you have learned in high school. But it's something that you should know. Maybe rarely you have such question that you need a real long division in the exam, so you need to review it, but it's rarely used in this course. So you use the line division, but after the line division, what do you get? You get the quotient and remainder. The idea of line division is that you can write Q as, no, the polynomial P as quotient times Q, Q times quotient. That's the conclusion of the line division. After you done this, you can write this quotient plus remainder. If you recall from high school, you get some equation like this. If I divide this equation, the whole equation, what do I have? I have P over Q. If I divide the whole equation by Q, to construct P over Q on the left, or multiply by 1 over Q, you get P over Q on the left. On the right, you get this divide Q, which is just the quotient, plus remainder over Q. So that's the first step of partial fraction method. If the degree of this is lower than the bottom, then you skip this step. You don't have this step. But if the degree of top is higher than or equal than the degree of the bottom, you should do the line division to write it as this. What's the point of writing P over Q as this? It's the idea is that you have some polynomial. This is a polynomial. You can find antiderivative of polynomial. That's no problem. But this fraction, it's again in this form where the degree of the top is now less than the bottom. So if the degree of top is not less than the bottom, using this process, you make it less than the bottom. In the next step, I'm assuming that the degree of top is less than the bottom. So note that in the line division method, always degree of remainder is less than degree of Q. So I have degree of remainder is less than degree of Q. So in this fraction, it is guaranteed that degree of top is less than the bottom. Okay, I'm done with this step. Rarely we use such a step in this. We have this step, but rarely we use the full line division. We don't need usually line division. We can do it with some easy computations by like I show you in the examples. The next step, it's assuming that degree of top is now less than the bottom. So step 2, it's now assuming that degree of top is less than the bottom. It's factor the denominator, the quotient. So factor qx as much as possible, such that you only get linear factors like ax plus b, a linear factor like this, or a quadratic irreducible polynomial, a quadratic irreducible term. What is a quadratic term? It's in general, it's ax squared plus bx plus c. That's a general quadratic term, but you can use quadratic formula on this. If you cannot use quadratic formula on this, that's called irreducible. With, what was the quadratic formula? Minus b plus minus root b squared minus 4ac over 2a. So you get nothing out of this if this is negative. So an irreducible quadratic term, it's a quadratic term with this to be negative, with b squared minus 4ac negative. If it is positive or 0, this means that this is factorizable. This quadratic formula, this quadratic equation is factorizable. You need to break it more. You should break it as much as possible until you get either linear or quadratic, which is not breakable. That's the idea. You may ask, you may have this question, is it possible always to do this? In practice, maybe no, but in theory, yes. There is a theorem in algebra that can be proved. We don't bother with the proof and the theorem itself, that it says that any polynomial with real coefficients can be factored like that, such that you have only linear terms or irreducible quadratic. So there is a theorem in algebra that you can do that. Okay. Now what's the next step? After factoring the denominator. After factoring the denominator, you have that qx, it's factored in terms like this or like this. For each of these terms, I need a fraction. I need a partial fraction. So let's, before showing that to you, look at here. The polynomial in the denominator, it's factored as this and this. Note that this is linear, this is irreducible. For each term in the denominator, in the factored form of denominator, I get a fraction. I want to express these fractions. Going back here, that's the idea. For every, you can ignore this. That's included in the second one. It's redundant, basically. So after factoring Q, look at different factors, distinct factors. For every linear factor, like ax plus b that I mentioned, maybe you have this factor 5 times, maybe 10 times, maybe 2 times, maybe only once. So you have some repetition. So you assume that you have a factor which is ax plus b and it's repeated n times, not more. Then in the partial fraction terms, you will have n fractions, the same number as it's repeated here. Each time you have n repetition. Each time you have this term with degree 1, 2, 3, up to n. And on top, you always have constant. These are constants, parameters. Why you have constant on the top? Because 1 degree lower than linear, it's a constant polynomial. 1 degree lower than degree 1, it's degree 0. Don't make mistake. I'm not having anything 1 degree lower than the whole thing on top. 1 degree lower than the factor. Here, having ax plus b to the power n, the factor term is just ax plus b. And it's repeated n times, but the factor is ax plus b. It's degree 1. So all of these, they have ax plus b terms, but some repetition, once, 2, or n times. It's a similar situation when we have irreducible quadratic term. That's an irreducible quadratic factor. It's repeated m times. So I have m partial fractions for it. For every degree from 1 up to m, from 1, 2, up to m, I have 1 partial fractions. And on top, I always have 1 degree lower than this. This is quadratic. 1 degree lower than that, it's linear. So on top, I have always linear, linear, with some unknown coefficients. These are, let me circle all of them. These are unknown coefficients needed to be found. These are the unknown coefficients. Also this one, if you have a single term, but you can ignore it. And this is a special case of that. So these are the unknown coefficients. How many of them you get? I get a rule of thumb, easy one, that you you make sure that you have those many unknown parameters. How many unknown parameters we get? The same as degree of Q. So total number of unknowns should be the same as degree of the denominator, Q. So you get many unknowns, as I circled here. Total number of them is the same as degree of Q. Next step is to find these unknowns. They are all real numbers, but unknown at this step. In the next step, I will find all unknowns. How do you find all unknowns? You just take the common denominator of all these terms to make them similar to this as one fraction. In the top, you get a polynomial with some unknown coefficients. It should be px. Putting the coefficients of different degrees. For example, the term in px, you have 2x squared. When you combine these, you get, for example, a1 x squared. Then the coefficient of x squared in these two should be the same. Then you find the unknowns. It's basically solving a system of equations in some unknowns in some equations. So these many unknowns and these many equations, it's a system of that you need to solve. You will see it in the examples. And the final step, when I found all these unknowns, is each of these examples are simpler problems that you can solve using previous methods like substitution and arctangent and these kind of things. Compute each of these antiderivative of each of these, and then add them up. You get antiderivative of the whole thing. Divide and conquer. This is the idea of partial fraction. It's very important technique and very powerful. Let's do some examples. First, let's focus on what partial fraction terms we will have. So in these examples, for all of them, degree of top is less than the bottom, and for all of them, the denominator is factored in the correct format that we want. What was the correct format? I have it here, such that I have only linear and irreducible quadratic factors. They are already given to you like that. So a step 1 and 2 is done for you. I want to do only a step 3 for these examples. Let's do a step 3. So look at the factors that I have. I have x plus 1, 3x minus 4, and x plus 2. All of them are linear factors. So I will have, for this term, I will have, what is the repetition of it? It's only once. So I will have only one term of that. And that term is x plus 1. What should be on top? An unknown, but unknown of what degree? This is degree 1. The factor is linear, degree 1. So on top, I should have degree 0 or constant. So that's one of the terms, contribution of this. How about for this? That's also linear. So on top, I have again a constant, 1 degree lower than linear, it's constant. Another unknown like that. How many repetition it has? 1. So only I use it once. How about this term? It is again linear, x plus 2. But so on top, I will have 1 degree lower than that, which is constant. I don't use the same letter. These are different constants, different unknowns. But what is the repetition of this? 3. So I need to have 3 instances of this with degree 1. Let me copy, or because I want to use another name, let me write it. With degree 2. And also with degree 3. That is the partial fractions. Next step that we don't do for these examples is to find these unknowns. Look how many unknowns I have. 1, 2, 3, 4, 5. What is the degree of denominator in the bottom? 5. That these two always should match. Let's do it now for this. So this is irreducible quadratic term. I dropped my pen. This is irreducible quadratic term. So I will have a factor contribution of it. But on top, this is quadratic. So on top, I should have 1 lower degree, which is linear. Ax plus b, a general linear polynomial with 2 unknowns, a and b. Contribution of the, if this was degree higher to 3, I would had more copy of this, but it's degree 1, so it's only that one. Now this one, linear term, so it's x minus 1, 1 degree lower than linear, it's constant, so I use this. Degree is 1, so I have 1 instance of it. Now this term, This is quadratic irreducible. So I will have x squared plus 5. 1 degree lower than quadratic is linear. Dx plus e. But this is repeated twice. So this instance also should repeat twice. After e, let's say f x plus g over x squared plus 5 with the degree 2. That's the partial fractions. Then I need to find these unknowns. How many unknowns I have? 1, 2, 3, 4, 5, 6, 7. Degree of this should be 7. Is it? Let's count. Degree 2 times 2, degree 4. Degree 4, degree 1, so degree 5, and 2 more, degree 7. 7 unknowns, degree 7 in the denominator. This should always match. Now the last one. 2x plus 3, it's one linear factor. 2x plus 3. One lower than linear, it's constant. This one, it's again linear. X minus 5 minus. One lower degree than linear, it's constant. Its repetition is twice, so this here also I should have 2 instances of it. And finally, this is irreducible quadratic. 1 degree lower than quadratic is linear on top. And this is repeated twice. So here also I have 2 instances of it. How many unknowns? 1, 2, 3, 4, 5, 6, 7. What is the degree of this? This is degree 4. This is degree 2. In total, degree 6 up to here. Degree 1, degree 7. That match. Before continuing to the next slide, let me give you a comment. Any quadratic term should be irreducible. That's very important. If this was minus 1, if you say minus 1, this is wrong. It's not correct. Why? Because if you had x squared minus 1 as a factor, this is not factor irreducible. This is irreducible to x minus 1, x plus 1. You shouldn't consider x squared minus 1 as one quadratic factor. That's wrong to do. You get wrong answer. What you should factor it as much as possible. So if it's reducible, it's wrong to consider it as quadratic. You need to write it as x minus 1, x plus 1, two linear terms. So only keep quadratic if it's irreducible. Again, what was irreducible? When the quadratic formula cannot be used. When b squared minus 4ac is negative. When it cannot be factored. Okay. Now let's move on to the computation of this. Now I'm focusing on, we have seen how to do partial fractions. Now step 4 is to find the unknowns. Now let's focus on finding the unknowns. This example, the partial fraction forms are given. It has 3 unknowns in it. My goal is to just find these unknowns. How do I find the unknowns? A step, I think it was 4, finding the unknowns. Yeah, let's do that. The idea is, as I mentioned, combine these into one fraction. What do you get? On the left, it's just as it is. Minus 3. But on the right, take the common denominator of this. What is the common denominator? Of course, it's the same denominator as here. X plus 1 squared x minus 3. So they have the same denominator. But when you take the common denominator, this term, it had x plus 1 previously in the denominator. But now I need one extra x plus 1 and x minus 3. So that becomes a x minus 1, x minus 3. if you multiply this fraction and also divide by x minus 1, x plus 3, the denominator becomes this. What about for second fraction? I already had this. The missing term was only x minus 3. So I only need to multiply and divide by x minus 3. So that's bx minus 3. And this term, the denominator had already this term. So the missing term is this. So I need to multiply and divide by this missing terms. So I get c x plus 1 squared. Good. So this means that because the denominators are the same, the numerators should be equal. This means 16x equals ax minus 1. By the way, this was plus 1 everywhere. Yeah, I don't know why I wrote minus 1 there. Let me check. Plus 1, plus 1, plus 1. Okay, good. Everywhere it's x plus 1. Ax plus 1, x minus 3, plus bx minus 3, plus c x plus 1 squared. This equals this. This is a polynomial that I know all the coefficients. This is the polynomial with unknown coefficients. I can find the corresponding coefficients from both sides. Let me do that on the next page. Then I show you an easy way to do it. So that's basically, do I have more space even? Yeah, let's do it there. So I want to write down the system of equation that I have and find the all unknowns. How many unknowns? A, B, C, 3 unknowns. So I should have 3 equations in 3 unknowns. So first, I expand this. What do you get? You get a x squared minus 3x plus x minus 2x minus 3 plus bx minus 3, or if you like to expand, it's bx minus 3b plus c x squared plus 2x plus 1. Then group the similar terms together. So for x squared, what do I have? I have ax squared, so that's ax squared. I don't have any x squared here, and I have cx squared here. So that's plus cx squared. For x term, I have minus 2ax from here, so minus 2a. From here, I have b, and from here, I have 2x. And finally, the constant terms. From here, I have minus 3a. From here, negative 3b. And from here, positive 1. This is the same as 16x. All of these are 16x. Comparing these, 16x is the same as 0x squared plus 16x plus 0. So this should be the same as this, 0. This should be the same as this, 16. And this should be the same as this, 0. So I get 3 equations in 3 unknowns. A plus C equals 0. 16 equals minus 2a plus b plus 2. By the way, I forgot something. I forgot that expanding c in this. So that's 2. The coefficient of x here is 2cx, not just 2. We have c here. And also the constant here, it's 1c. So it's just c. So that's 2c. And the final thing is that this should be 0. 0 equals minus 3a minus 3b plus c. Good. So I have three equations in three unknowns to solve. So you know, all of you should know how to solve system of equations. For example, from this one, you can find C is negative A. Then you can substitute that in these two equations and continue doing this to get the solutions. We will get the answers from this. If you solve, I will skip doing the solution. You get A equals minus 3, B equals 4, and C equals 3. I will do this in a simpler method. So that's one way to find the constants, writing down system of equation and solving the equations, n equations in n unknowns. Going back here, there is an easier way to find these coefficients. For every linear term, I have one of the unknowns for free given to me. For every linear factor. How many linear factor I have in this? 1, 2. So two of the unknowns, I can find it without solving any equations. How? Replace for any linear factor, there is a root of that. For example, for this, x equals 3 is a root. For this, x equals negative 1 is the root. If in this equation that I want to solve, I replace x with the root of the linear terms, one of the constants will be given to me. Let's try that. At one of the roots is x equals negative 1. At x equals negative 1, what do you get? Replace in this equation x equals negative 1. You get 16 minus 1, which is minus 16. A, this term will be 0 times 0. So this term will be completely 0. Because x plus 1 is 0. When x is negative 1, x plus 1 is 0. That's 0. This is also 0. And the middle term is minus 1 minus 3. And the last term is also 0. I have this simple equation that gives b to me. This is minus 4. And b will be minus 16 over minus 4, which is 4. That's the same b that I got from solving the system of equation. I can find one other unknown as well very easily. Look at this linear term. The root of it is 3. So I can do the same thing at x equals 3. At x equals 3, you get 3 times 16, which is 48. Or let me first write it 16 times 3. When I put 3, every x minus 3 term is 0. So this is 0, this is 0. So these two terms disappear. 0 plus 0 plus, I only put 3 in this, which is non-zero, which is 3 plus 1 squared. That's 4 squared, 16. So the answer is 16 times 3 over 16, which is 3. So C is 3. Can I find the third unknown by substituting a number? No, we have only two linear terms. So we can find only two unknowns. We already did. I found B and C. For the last one, you just write down this system of equation with all the knowns that you know, or everything that you know. Then you have less unknowns to find and it's easier to find. So expanding this, I got this. Yeah, I had this. I had this expansion. Did in the next page. Okay. That now I know that. Let me say from the computation on the next page. From the computation on the next page. We got this. But instead of considering a three equations in three unknowns, two of the unknowns I already have in my hand. B is 4 and C is 3. Let me put B 4 and C 3 in these equations. So what was it? C free. C free. And B4. Even I don't need the rest of these. Only this equation gives a what I want from A. So basically, let me also copy this, but write only the first one of them. Basically, we have this equals this, hence A plus C equals 0, but C is known to be free. That's enough to find A. Since C is free, I have A equals minus 3. And that is this third unknown that we found. That's fine if you do go for the general methods, solving system of equations, but that's longer. You need some computations that I skipped here to solve this system of equations. This is faster if you can use it. Okay, next example. It's basically doing the same thing, practicing more. Second example, again, finding the unknowns, focusing on only a step 4. So what was the process? Now I do it faster. You have seen one example of it. Combining these into one fraction, you get x squared plus 9 times x plus 3, then ax plus b times missing term in the denominator is x plus 3 plus c times the missing term in the denominator is now x squared plus 9. So I get an equation. 18 should be this. Copy this. Can I find any, if I have 3 unknowns, A, B, C. Can I find any of them without solving any system of equation? Yes. For every linear factor, I can find 1. How many linear? This is not linear factor. This is a linear factor. I have 1 linear factor. I can find one of the unknowns easily. So at root of this linear factor, x equals -3, we have this equation is putting -3 in it, that's 0 because x plus 3. Then putting -3 in this, you get 3 squared, which is 9 plus 9. So you get 18, C is 18, so C is 1. I found one of the unknowns. Put that in this and expand it. For the rest, I need to solve system of equation. So 18 equals AX. There are some other techniques to find other unknowns as well, but I don't want to make it a lot complicated than this. So just for the linear terms, use this. The rest, just expand and compare the coefficients on two sides. So x plus 3 plus c is 1. C is 1, 1 x squared plus 9. Expanding this, that's ax squared plus bx. Oops. What? Oh, it jumped to the first page. Let's go back. We were here. No. Yeah, we was at the middle of this computation. We were at here. Okay, so that was x squared, then 3ax, then bx, then 3b, 3b, not d, plus x squared plus 9. So that means that 18 is grouping terms, x squared terms are these, a plus 1 x squared. X terms, I have 3a, b, and that's it. X. Constant terms, I have this and this, 3b and 9. Comparing the coefficients on the left and right, this is a quadratic polynomial. And here, if I want to write it as a quadratic polynomial, it's plus 0x plus 0x squared. So this should be 0. A plus 1 should be 0, hence A should be negative 1. What else? I know that this should be 18. I use the one that it has only one unknown in it. You can basically use this as at this step because I already have found A. Whatever you use, you get the same thing. If you use this, you get 3A plus B equals 0. The coefficient here is 0. Hence, B equals minus 3A, but A is negative 1. So it's minus 3 minus 1, which is 3. So B should be 3. Using this, give the same thing to you. Let's try it. 3B plus 9 should be 18. That means moving 9 to the other side, 3B should be 9. And B should be 9 over 3, which is 3 again. Okay. So we found ABC. Okay. Now let's focus on evaluation of last step. Up to now, we did all steps up to step 4. Step 4 was to find these unknowns. Now assume that we found some unknowns and we have the partial fraction without the unknown in it. The last step, step 5 of the partial fraction method, was to evaluate each of the simpler integrals and then add them up. For this example, let's just do a step 5. In the next lecture, I do all the steps together, but for this first lecture, we do a step by step. We focus on one step. Okay, so if I want to compute this integral, that's huge. Let me don't write it and just flag it and say this equals. If I want to compute that integral, that would be the same as integral of this, integral of this, integral of this, and integral of this. So basically, I need to find antiderivative of each of these terms. Let's do them one by one. What is antiderivative of this? That's very simple substitution, or even without substitution, many of you could guess that this is antiderivative of that. Because and derivative of ln x is 1 over x. I have 1 over x minus 1. So derivative of, I need ln x minus, absolute value x minus 1 to get derivative of that. If you are not comfortable with guessing this, do you remember the first problem, warm-up problem that we did? That's the technique that you should use in general. You do substitution, u equals the denominator, and find this. This one also, you could do it without substitution and just guessing that I should have ln of this thing, but adjusting the coefficient on the back to make sure that the coefficients match. Whatever you're comfortable, substitution or just by guessing, a wise guess. Okay. Now this one. What is antiderivative of that? It's better to write this as 2x minus 1 to the exponent negative 2. Writing it as a power term. Bringing this to the numerator, I have to the exponent negative 2. Then using, if you like, a substitution, u equals x minus 1, or just do it directly. The antiderivative should be minus 2 minus 2. Increase the exponent by 1, x minus 1 minus 1 over minus 1. Note that I don't need any coefficient adjustment because this is just x. Derivative of x minus 1 is just 1. If this was 2x minus 1, then I would have some extra coefficient adjustment. To find them, if you like, you could do substitution. This one, what would be that antiderivative of that one. Antiderivative of this, it's similar to this. Either you do substitution u equals this, or you see that, oh, I have 1 over this, so it should be ln absolute value 2x plus 1. But if I take derivative from this and compare it with that, I would have derivative of this, it's 1 over 2x plus 1 by chain rule, also times derivative of inside, which is derivative of 2x plus 1 is just 2. Comparing this with this, I don't have that 2 there. So I need a coefficient 1 over 2 on the back of this to make sure that after taking derivative, with this coefficient here, this and this cancel, and I get exactly what I want. That's the way to do it without substitution on air. Or if you like, do the substitution, u equals this, and follow the substitution method. What about this one? For this one, you need to do a little bit trick on it. So first, do I have, how much space I have? Yeah, let's compute this on the next page and then substitute it here back. Okay, so I want to focus on integral of 2x minus 3 x squared plus 4. So if there was no x term, I knew how to do it. That's the formula that you see here using arctangent. Also, if there was no constant term here and it was just this, I know how to do it because that derivative of this is on top, which I can use a substitution on it. So it's better to separate this into two integrals, 2x x squared plus 4 and minus 3. Let me write 3 on the back. 1 over x squared plus 4. So I wrote this as two integrals. If it's more clear, write 3 here anyway. At this step, let me write it as this. Plus minus 3 or minus 3. Okay, so what is antiderivative for this one? That's simpler. Antiderivative for that one, it's just using this formula. Using that formula, I have 3, which is on the back. My a is 2 here. A squared is 4, which is a is 2. So when a is 2, I have 1 over a, arc tangent x over a. A is 2 plus a constant. That is antiderivative of the second term. Let me combine these two as 3 over 2. 3 times 1 over 2, it's 3 over 2. That's the antiderivative of second term. What about the first term? I already mentioned the idea. I see something whose derivative is on top. So I need to do a substitution. U equals x squared plus 4. If you do that, you get u, that's u, and this is du. Note that du is 2x dx. So I have integral of 1 over u du. Antiderivative of this is ln absolute value u. I don't need this c here because still I have one unknown, one indeterminate integral. When I'm all the indeterminate integrals are disappeared, that's the time that I add a constant. Now plus c, because there is no indefinite integral anymore in it. Okay, that's not my final answer because my final answer should be in terms of x. Where is it? This function. So that's u should be replaced in terms of x, and that would be, what is u? U is x squared plus 4. So it's ln absolute value x squared plus 4 minus 3 over 2 arc tangent x over 2 plus c. One last comment is that x squared plus 4 is always a positive number. It's always positive. It's never negative. So absolute value is redundant. If you like, u is x squared plus 4 I'm substituting, and it's always positive. So you don't need absolute value. That is the final answer for this term. Now copying this here after this term plus this minus this. So this whole thing is antiderivative of this scary fraction. Using partial fraction, each component is very easy to compute. That's the power of partial fraction. Great. So that would be the answer for this one. And that was the last question for first lecture. So let's just jump. It's continuation of previous lecture. Let's just jump to the next lecture, which is up to now, as I mentioned, we have seen what's the partial fraction methods in general, step 1, 2, 3, 4, 5. But we did only one step at a time in an example. From now on, we do one whole partial fraction question all together from step 1 up to step 5. That's the content of next lecture. So as a first warm-up question, what are the partial fractions of this? So this is irreducible quadratic. So let me first copy the fraction here. 3x, x squared plus 4, x squared minus 4. I want to write the partial fractions. This is an irreducible quadratic. So for that term, I will have a linear term on top, ax plus b, 1 degree lower than this. It's repeated once. This is also repeated once. This one, if you think that, oh, that's quadratic, let me put it here. And let me put a 1 degree lower than this, which is linear on top. That's completely wrong. So this is completely wrong answer. Why? I emphasized on it in previous lecture already. If something is not irreducible, you cannot consider it as quadratic. You need to break it as much as possible. This x squared minus 4, it is not irreducible, but it is x minus 2, x plus 2. So instead of having a quadratic, I have two linear terms. For each of them, I will have a partial fraction with one lower degree than linear. It's constant term on top. If I want to keep the order of them, that was minus first and then plus after. So that is the partial fraction. Which one will be the correct one? I need to search for it. It's either this or this, but ax plus b. So it should be this one. C is the correct one. This is just copy of what we have seen before, just for review. So the steps. By default, if degree of top is more or equal the bottom, you have one extra step that most of the time it's not there, using long division to write this as a polynomial plus another fraction, another rational function, which in this new rational function, degree of top is actually less than the bottom. So in the step 2, I can assume that degree of top is less than the bottom. So in after step 1, degree of top is less than the bottom. if then the next step is to factor the denominator as much as possible, such that you only have linear or irreducible quadratic. Then third step is to write down the partial fractions with the unknowns. How many unknowns you get? The same number as degree of the bottom. In the step 4, you find these unknowns. In step 5, after finding the unknowns, these are known fractions. You compute each of these integrals, antiderivatives, and then add them up. So that's the whole partial fraction method. Now let's do it for this whole question. This is the first question, that degree of top is not less than the bottom. So we have actually a step 1. Let me focus on step 1. Just as a review, let's do line division, but as I mentioned, we usually design the questions in this course such that you don't need actually the line division. For example, for this one, you can easily, by some simple computation like trick, without using line division, rewrite this as whatever we want. But first, let's review line division for this question. So I will put this on the left, minus x3 plus x squared minus 9x plus 9. I will put this here, 2x cubed minus 2x squared plus 18x minus 8. Okay, and then I compare the highest degree term here and here. And I ask myself, what should I multiply by this to get that? Or divide this by this? What is the answer? I need to multiply this by a negative sign and 2 to get 2x cubed. So I will write my finding here, negative 2. It's what I should multiply by this to get this. That's the idea of the line division method I'm just reviewing. Then I multiply this by this whole thing and write it on the bottom of this. Negative 2x cubed. I'm just multiplying this by that. Then negative 2x squared. Negative 2 times negative 9x, which is 18x. Negative 2 times 9, which is negative 18. And that's negative 2 times this, written here. Subtract these two polynomials from each other. By the way, this was positive. Negative 2 times negative x cubed. It was positive x cubed. Okay, subtracting these. This minus this. You get just cancel, 0. This minus this, they are the same, cancel. This minus this, they are the same, they cancel. But this minus this, it's negative 8 minus minus, which is plus 18. 18 minus 8, it's 10. So this is the remainder. And this is the quotient. So what is the upshot for this line division? Step 1, line division, is to rewrite this fraction that would be 2x cubed minus 2x squared plus 18x minus 8 over minus x cubed plus x squared minus 9x plus 9 as quotient. After the line division, what happens? Recall that this was previous lecture, I mentioned it here. After the line division, here we have that the fraction that we have is the quotient plus remainder over denominator. That's what the upshot of the long division is that. So if I use that, it's the division statement basically after the long division. I have quotient -2. This could be a polynomial. In this case, it's simple. It's just a number. -2 plus remainder over the previous denominator. That's the conclusion of long division. After the long division, I can write down that. So that is the long division step. What was the point of doing this? The degree of top was not smaller than the bottom. By doing this, I have a polynomial that I can handle its antiderivative, and I have another fraction with the same denominator, but now degree of top is smaller than the bottom to reduce that. Why I need to do that? Because in these steps, in this partial fraction method section, I assume that degree of top is less than the bottom. Otherwise, if the degree of top is not less than the bottom, you cannot use this method, partial fractions. The reason that you can write any fraction p over q that degree of top is less than the bottom like this, it's a theorem that you can prove in algebra only if degree of top is less than the bottom. Okay, so I need degree of top less than the bottom. Anyway, that was long division. I mentioned that if you forgot long division, you can still do this for this problem, not for a general problem, for simpler problems. How can you do that? You would see that basically it's the same idea as we did here. You would see that, oh, this is a cubic polynomial. On top, I have also cubic polynomial. So let's write top as a multiple of the bottom. I need to multiply the bottom by -2 to get the same coefficient as top. -2 times negative, it's 2. It's basically how we found this quotient. So the idea is, look at what is -2 times the bottom. -2 times the bottom, -2 times bottom, it is 2x cubed minus 2x squared plus 18x, -2 times 9, -18. That's -2 times top. So I can write this polynomial, compare this polynomial and this polynomial. Oh, you see that three terms are actually the same. So the last term that I have, I can adjust it as -18 because I want -18 plus 8. That's this plus 10. That's the same as 8. I had -8. I add 10, subtract 10 to make this -18. So if I do that, this part, it's just negative. The top is -2 times bottom. So it's -2. You get this out of it. And this part, it's what you get this out of it. So without any reference directly to long division, it's basically the long division that we are doing. But you can just by thinking process, you can handle this simple long division example without doing long division. That's also possible. Try to make the top as a multiple of the bottom. Then you compare the multiple of the bottom that is good to compare to top according to the highest degree terms, and then see what adjustments you need. Maybe you need to add, subtract something to get the coefficient, the constant term right, or get the x terms right. That could possible. You could have, for example, let's another example of this method works. For example, let's this to be actually 8x, not 18x. Then I would compare this with this And I would see that, oh, I have 2x cubed. That's good. Negative 2x squared. That's also good. But this one, it's 18x. Here I have 8x. So I would add 10x and subtract 10x. In other words, I would combine this with that to get 18x, and I would have some extra negative 10x. The same I would do for that. Then I would complete this and with some extra terms that appear here. That's also possible. Whatever you prefer. If you are comfortable with long division, definitely go for it. Otherwise, you can do these kind of tricks to uh, escape doing long division. Okay. Now we are done with step 1. So let's do a step 2. What is a step 2? It's factoring the denominator. Hopefully that's given to us. This is a step 2. Let me use another color. Because it was not as straightforward as you think. It's not hard, but I need a try and error and again long division, these kind of things to factor this polynomial. So this factorization that is given is a step 2. Okay, good. Now step 3. Step 3 is writing the partial fractions. Let me. Do I work with the original fraction? This? No, I work with this. Because to do the partial fraction step in step 3, I mentioned one important assumption is that degree of top should be less than the bottom. Degree of this is not less than the bottom. That was the whole point of step 1. To find a new fraction that degree of top is actually less than the bottom. So I need to do partial fraction of only this term. Let me copy this and paste it on the next page. Partial fraction of this. First, I need to consider this as a factored denominator, as a factored denominator. Applying a step 2 to the denominator, we get this. What is it? It's 1 minus x squared plus 9. 1 minus x squared plus 9. Then writing the partial fractions terms. First term, first factor, it's a linear factor. So I will have it with 1 degree less on top. 1 degree less than the linear, it's constant. Repetition is once, so I have only one instance of it. Now this term, it's a irreducible quadratic. So I will have that with 1 degree less, which is linear on top. How many repetition? It's only once, so I have only one term. That's a partial fraction. That's a step 3. Step 3 is to write these partial fractions. Step 4, find ABC, find the unknowns. Let me, before do that, check that my number of unknowns match with the formula that I mentioned. 1, 2, 3 unknowns. What is the degree of denominator? It's 3. Good, they match. So I haven't done any mistake, probably. Now step 4. Find unknowns. To do that, if you remember, I needed to take the common denominator of this. So I have this up to now. Let me copy it. But I can combine these into one fraction. Then I will have 1 minus x squared plus 9 on top. The missing term in the denominator of this is this other term, x squared plus 9. The missing term in the denominator of this is 1 minus x. So I multiply this by 1 minus x. So now this is the same denominator. So the numerators should be the same. I get a system of equations coming from this should be 10. Let me actually find the unknowns on the next page. But before doing that, is there any of three unknowns that I can find easily without writing system of equation for it? So as many linear term as you have, you can find them easily. So this is not linear, but this is a linear term. So I have only one linear term in the factors of denominator. So one of the unknowns, it's very easy to find. How? What is the root of the linear term? It's 1. By putting x equals 1 in this equation. So let's do that on the next page. At x equals 1, you get 10 equals a. X equals 1. 1 plus 9 plus this term is 0 because of the second term is 0. So that's 10a equals 10 or a equals 1. Good. For others, I need to write system of equations. So let me expand this with a equals 1. When a equals 1, this is with 1 here. Let me continue using red with 1 and now expand it. I get x squared plus 9 and expanding this, that's bx minus bx squared plus c minus cx. In other words, x squared term. What do I have? This one and this one. It's 1 minus bs, 1 minus b. X terms, I have this and this. So it's b minus c. And constant terms, I have this and this. So it's 9 plus c. This should be 10. As a quadratic, this is quadratic. So on the left, as a quadratic, it's 10 plus 0x plus 0x squared. Comparing the coefficients, this should be 0. So b should be 1. 0 should be 1 minus b. b should be 1. And let me use this because it has one unknown in it. 10 should be that. 10 should be 9 plus c. And c should be 10 minus 9, 1. Actually, a, b, c are 1. I found all the unknowns. So that's end of uh, the step 4. Let's summarize up to now what we have on the next page. Originally, I had this huge fraction. Let's combine everything from step 1 up to step 4 up to now. So that was the original fraction, this, which at first I wrote it as this. So let me actually copy the whole thing. Good. But then I break this into partial fractions. I break that into the partial fractions like this. And I found A, B, C. All of them are 1. So that term is now this with A equals 1, B equals 1, C equals 1. Basically, I can write that as also negative 2. That was the first step. And then negative 2 plus 1 over 1 minus x plus, when b and c are 1, this is x plus 1 on top, over x squared over 9. This is what I got. So this very ugly fraction, it's this much simpler one. Now, to find antiderivative of that, I just need to focus on these terms and find antiderivative of these terms. Okay, good. Now, step 5 is to compute antiderivative of these and hence antiderivative of this. Step 5. And let me first write antiderivative of each of these terms separately. Antiderivative of minus 2, it's minus 2x plus c. Antiderivative of this term, 1 minus x dx. It is ln. If you like, let's do substitution for this, just to make sure that everything is clear. Let's do all the details. Take this to be u. Take u to be 1 minus x. You can use without substitution, like a few examples before that I explained on air. But like as a change of favor, let's just do substitution for this one. U equals minus x, then du. Its derivative of 1 minus x is minus dx. So this one, it's u, and this one, it's minus du. After the substitution is 1 over u d negative du. So antiderivative of this will be ln absolute value u with a negative sign on the back, this negative sign, plus a constant. And replacing u with this, you get minus ln absolute value 1 minus x plus c. If you like, this is the same as absolute value. If you like, 1 absolute value x minus 1 and absolute value 1 minus x, they are the same, whatever you prefer. There is no preference. Let's keep it as it is. Okay, good. So we got this. That's the answer for this and this. Now let's find antiderivative of the last one. To do that, it's exactly similar to one of examples that we did here. Antiderivative of this such term that it's x squared plus a constant and a linear term on top. It's better to consider it as like two separate terms. One with x term on top, which is derivative of denominator, and do the substitution for it, as I did here. The other one, considering only constant on this term and using this formula. So that's what I should repeat doing it. Let's go back here. Yeah. So I need to consider this and this as two separate integrals. So first, integral x over x squared plus 9. How would I do this? Derivative of this up to a constant is on top. So I choose this to be a new variable and I do a substitution. U equals denominator x squared plus 9. Then du is 2x dx. So this is u and this is x dx. It's half of du. So that's integral 1 over u half of du. Antiderivative will be half of ln absolute value u plus c. And don't forget to replace u in terms of x, but u is x squared plus 9, which is always positive. So I replace it, but I also drop absolute value. That's completely redundant. Here I cannot do that. But here I can, because x squared plus 9 is always positive. Here 1 minus x is not always positive. So it's half of ln absolute value x squared plus 9 drop absolute value, you get just parentheses x squared plus 9 plus c. That is the answer for this part of this. Now the last part, this integral 1 over x squared plus 9 dx. I use just the arctangent formula. A here is, this is a squared, 9. So a is free. So the answer is 1 over free arctangent. I'm just using the formula. If you like, you can do a substitution and solve it, but you can also use the formula. X over 3 plus c. And that is the answer for the last piece. What is the answer for the original problem? It's just sum of all these with only one constant. Don't add 4 or 5 constants. One constant for the whole integral is good. So I don't have space here to do, but let's go back or let me add a new page after that. Okay, then an empty page. So the final answer is integral of this indefinite integral of this is first answer for this, which is just negative 2x. Then the answer for this, which is this. Notice that I don't add the constants until very end, and just one constant for the whole integral. And finally, no, this, which I did it in 2 steps. One part of it is this. And another part of it is this. I need also one constant, so let me take this constant. Plus, plus. So this is the final answer. Is it clear? See, this is very ugly, like fraction that it's not easy if you don't know this method, systematic way of doing breaking fraction into smaller pieces and solving these smaller pieces. It looks like a very hard problem, but when you do a step by step, it's very like mechanical to do it. Okay, now we have the last slide for today, which is these two. We are asked to see what should I do. In general, when you have polynomial over polynomial or rational function, which is both of these, partial fraction is the general method to use. But sometimes there is a faster way to do it. For example, in this question, if you look at denominator of this, what is derivative of denominator of this? Derivative of, if you take derivative of that, that's 3x squared. Let me do it like this. X cubed plus 6x derivative. That's 3x squared plus 6. And I can factor 3 out of these to get x squared plus 2. You see that up to a constant coefficient, that I don't care, derivative of the denominator is on top. So that's a sign that substitution is the best and the most efficient way of doing it. Of course, you can use any method, general method that you like, but it would be redundant basically. Doing all partial fractions and computations, it will be redundant because I have a substitution method that can give me the answer in one step, and by taking this to be u. So only for this one, only partial fractions, only for 2 is good. For 1 you can use, but that's not the best way to do it. It's actually the longest way to answer this question. The fastest way or best way to answer this question is to use substitution. So if you like, let's do actually solve this question. If you take u to be x cubed plus 3x, then du is what I have here, 3x squared plus 2 dx. So basically, this is u. If this is u, then this is this part, which is du divide 3. It's 1 over 3 du. Hence, I have 1 over u, 1 over 3 du after the substitution. You get 1 over 3 ln absolute value u plus c. And replacing that u with this, is this necessarily positive? No, not necessarily. So I can't drop absolute value. I need to keep absolute value. 1 over 3 ln absolute value x cubed plus 6x plus c. That's the answer for the first one, which I haven't used any partial fractions. But let's solve the second one as well as the final example for today. Okay. So first, so I should use partial fractions methods. Step one was to, if degree of top is more than the bottom, do long division. But degree of top is less than the bottom. So skipping step one. There is no step one here. Step two, factor the denominator. Let me first copy this integral here. That I want to do. Integral x squared plus 3x plus 12 over x squared, x cubed plus 6x dx. That is what I want to compute as last example of partial fraction for today. So no step one. Degree of top is less than the bottom. So I don't need step one. Now step two. Step two is factoring the denominator. That's easy one because there is a common factor x, and then you get x squared plus 6, which is irreducible. I cannot break this anymore in real numbers. Okay, step 3, writing the partial fractions for this fraction. If I write the denominator as a factored form, okay, I will have a linear term, which is x. 1 degree lower than linear, it's constant on top, plus. The repetition of it is 1. If it was x free, then I would have bx squared plus cx cubed as well. But now it's just multiplicity 1. So I have only one instance of this. The next term is irreducible quadratic, x squared plus 6. 1 degree lower than quadratic is degree 1. So I have bx plus c. Repetition or multiplicity is 1, so I have only one instance of it. How many unknowns I have? 1, 2, 3. Degree of denominator is 3. Good. Step 4, find ABC. To find ABC, let me expand let me combine these. Then I get a x squared plus 6 times plus bx, that's not enough space, bx plus c times x, the missing term in the second denominator, over the denominator x squared plus 6. comparing this and this fraction and this fraction, they have the same denominator, so they should have the same numerator as well. So putting these two equal to each other, step 4, it's that this equals this. And I need to find A, B, C from this. Can I find any of them with the fast method of not creating the whole system of equations? As many linear factors as I have, I can do that. How many linear factors I have? Only one. So I can find one of the unknowns. What is the root of this linear factor? It's 0. So I put x equals 0 in this equation. Then I get 0 plus 0 plus 12 equals a. 0 plus 6 plus this whole term will be 0 because of this x. So 6a equals 12. Or a equals 2. I found one of the unknowns. Now finding the other two, I need to expand this. Let me expand that. X squared plus 3x plus 12. A is 2. And expanding this, you get bx squared plus cx. So basically this is x squared. I have 2x squared, bx squared. 2 plus b x squared. For x terms, I have only one, cx. And for the constants, I also have only one, 2 times 6, which is 12. Compare this and this. 12 should be 12, which is. If it was not, means I did some computational mistake in previous steps. 3 should be c. So c should be 3. And the coefficient of x squared here, it's 1. That should be 2 plus b. So 1 should be 2 plus b. Hence, b should be 1 minus 2, negative 1. Now that I have a, b, c, I have the factored partial fractions form. So the conclusion of step 4 is what was a? A was 2. B is negative 1. And C is 3. Okay, and the original fraction was this, which is the same as this, but the denominator is in not factorial form. It's basically the same, but we have this. That's the upshot for conclusion of step 4. Now step 5 is to actually integrate these. Step 5 is to put integral sign everywhere on this. So I need to compute this and this. The first one, it's very simple. Integral 2 over x. It's just 2 ln absolute value x plus c. Good. But to do this, this is the third time today that you see this trick. It's x squared plus a constant. You need to do it in 2 steps, this and this. For the first part, you need to do a substitution, u equals denominator. For the second part, you need to use arctangent. So first, considering this term, minus x over x squared plus 6. I do a substitution, u equals x squared plus 6 Why? Because derivative of this, it's on top, up to a constant. 2x dx. So this is u, and this is only x dx part. It's half of du. X dx is half of du. So you have integral minus 1 over u, half of du, which is minus 1 over 2 ln absolute value u plus a constant. And replacing u with this, note that x squared plus 6 is always positive, so you can drop absolute value. U equals x squared plus 6, which is positive. You get ln without absolute value, x squared plus 6 plus 6. That's the contribution of this. Now this integral free x squared plus 6. That is free 1 over x squared plus 6. But if you remember the formula, it was x squared plus a squared. So let me write this as something squared. 6 is root 6 squared. So my a is root 6. Using that formula, it's free 1 over a arc tangent x over a. That's the answer. So the final answer for this whole integral is just collecting everything in one piece. I have this one without c. Okay, and then I have this one. And finally, I have this one, which is better to write as that 3 and root 6, combine it as 3 over root 6. Or even you can write this root 6 as root 2 times root 3 and partially cancel root 3 and 3. Okay, that would be the final answer for this question and the last question in this lecture. Okay, thank you everyone for listening or watching, and see you next week.